Lara Ismert, who will talk about a covariant Stone von Neumann theorem. And I'd just like to say we're especially grateful that she was willing to get up at something like 7 a.m. her time to give this talk. So we'll forgive her if she seems a little sleepy. Anyway, please take it away, Lara.
Thanks, Karen. Yeah, thank you guys so much for having me. This is a really nice opportunity and to get to interact with people that I've never met before, most of you. So that's very cool. Thank you. Yes, and also I told Karen I was like, oh, I wake up early all the time. Don't worry about it. And this morning I'm particularly tired, so do forgive me. Okay, so this is joint work with Leonard Huang, who is currently in the United States at the University of Nevada, Reno. And in March, this work was published in Communications Math Physics, if you want to see that, the full paper. So this project's based on a pretty historical problem. The question basically boils down to, is every pair of self-adjoint operators on a Hilbert space and we want to assume that this pair satisfies the Heisenberg commutation relation. Is this pair necessarily unitarily equivalent, in some sense, to the canonical Schrodinger pair? So let me introduce what all of that means. I'm assuming a lot of you are familiar with this, so forgive me if you are very familiar with this problem. So the Schrodinger pair, the Hilbert space that we're looking at here is L2 of R, and the pair of self-adjoint operators are, I'm being pretty sloppy with notation because of course P is an unbounded operator, and so the vectors F come from some proper subset of the Hilbert space, and Q applied to a vector is multiplication by the input, and that's for all vectors coming from the domain of this unbounded operator. But on their respective domains, they are self-adjoint operators, and they satisfy the Heisenberg commutation relation, which means if I look at their commutator and I apply that commutator to a vector that's in some sort of a common domain that they both share, it simply looks like multiplication by the scalar I. And the common domain that I like to think about is the space of Schwartz functions, rapidly decreasing functions. So there's other common dense domains on which this will work, but this is a nice one. Okay, so a generalization of the Schrodinger pair would just be a pair of self-adjoint operators, A on some domain that takes vectors in its domain back into some Hilbert space H, some other operator B that takes vectors from its domain back into the Hilbert space H, and I'm going to assume both of these are self-adjoint with those domains, and we assume that there's some subspace K of the Hilbert space that contains the, that is contained in, I should say, the intersection of these two unbounded operators domains. And I want that to be dense in the Hilbert space. And for all vectors in that subspace, that pair of self-adjoint operators commutator acts as multiplication by I. Okay. So generally speaking, these aren't as easy to come by as you might think. The requirement that these two unbounded operators A and B share this subspace K that's still dense in the Hilbert space, that's not always a given. And then you expect also on that space for their commutator to satisfy this relation. So it turns out that even under these conditions, having a pair of self-adjoint operators A and B that satisfy the Heisenberg commutation relation on a dense subspace K, that is not enough to classify them and say that they are unitarily equivalent to the Schrodinger pair. So really what one needs is more information about the subspace Ks, more stringent conditions. So the main strategy of decades of work is to essentially study this subspace K and determine sufficient conditions on it that would allow you to integrate the self-adjoint operators relation, the Heisenberg commutation relation, to a relation that is satisfied not by A and B, but by A and B's unitary family given by Stone's theorem. So A corresponds to some unitary family by Stone's theorem, and B also corresponds to some other unitary family by Stone's theorem. And so what you would hope, let me call this one R. So what one hopes is that, I'm gonna have to subscript S's with S's. That's not gonna work out very nicely. So let's call our scalars R. Okay, so you want this integration of the relation to the unitary family to satisfy what's known as the Heisenberg commutation relation. So when we swap the order of the unitaries SR with RT, we can do that, but with the expense of e to the ITR. Okay. And the reason that this is the strategy, a strategy, I should say, that is often looked at is because these pairs of unitary families, R and S, which satisfy the Weil commutation relation, are classified. So the Stone-von Neumann theorem goes by some other names like the von Neumann uniqueness theorem, but these pairs of unitary families are unique up to a direct sum of copies to the unitary families for the Schrodinger pair. So I'll state that formally. And in fact, the Stone-von Neumann theorem holds not just for unitary representations of the real line, but also for unitary representations of a locally compact abelian group. So here on out, G will be a locally compact abelian group. So here's what the Stone-von Neumann theorem says. If I have a unitary representation of the group G and a unitary representation of the Pontryagin dual G hat, and they intertwine in this way. So here again is the Weil commutation relation for a locally compact abelian group. Then there is a unitary W going from the Hilbert space on which R and S are represented over to a direct sum of copies to the Hilbert space L2 of G, such that R gets intertwined to equal a direct sum of copies of U, S gets intertwined by the same unitary to equal a direct sum of copies of the unitary V, and U and V are these canonical unitary operators. So U is left translation by elements of the group G, and V is multiplication by characters gamma. And this is e to the I XP. So that is the unitary family you get when you, via Stone's theorem for the momentum operator P, and these are the, I'm definitely playing poorly with notation here, so just ignore me. I'm exponentiating group elements. If they were real numbers, Stone's theorem would give you this, this relation. So this would be e to the I gamma Q if G were the real numbers. Okay, great. So some language that we'll end up using throughout. Anytime you have a pair of unitary representations R and S, which satisfy the Weil relation, in literature, this is called a G Heisenberg representation, which is kind of unfortunate. because it should really be a vile representation. But so we have one of those, and we have this canonical G Heisenberg representation, which we're calling the Schrodinger representation, because those unitary operators come from the Schrodinger pair. So as a corollary of this, if you've got a Heisenberg pair, so A and B satisfy the Heisenberg commutation relation on some Hilbert space H with a common dense domain K, and you know that that subspace K is nice enough for that relation to integrate to their unitary family, then by an application of the Stone-von Neumann theorem, you immediately know you can essentially go up to the unitary families. Stone-von Neumann theorem says you've got this unitary equivalence, and then you can differentiate them back down to the self-adjoint operators to say that your original Heisenberg pair is unitarily equivalent to a direct sum of copies of the Schrodinger pair. Okay. So that's all historical stuff. And here's what Leonard and I set out to do. We wanted to extend the Stone-von Neumann theorem to unitary group representations on Hilbert Seastar modules. Seemed like a natural next step to take. And then once we were in the land of Hilbert Seastar modules, there's of course this ambient Seastar algebra that is acting on the module. And we had a locally compact abelian group. And so we thought, can we somehow also involve a uniqueness statement about representations of Seastar dynamical systems onto Hilbert Seastar modules? So that is what today's talk is going to focus on. All of this is kind of a prequel to something that Leonard and I are working on right now, which is working towards a classification of what I'll call Heisenberg pairs on Hilbert Seastar modules. So, so pairs of self-adjoint regular operators on a Hilbert Seastar module, which satisfy the Heisenberg commutation relation on some sort of dense domain. Okay. All right. So the main theorem that we were able to produce wasn't as general as we were hoping for in terms of generalizing the Stone-von Neumann theorem, but we were able to say this, and after I state this, I'll have to give you some definitions. But we said every dynamical system of the form K of H, our locally compact abelian group is R alpha, so every this dynamical system Heisenberg representation. So instead of having a group G there, we have a Seastar dynamical system, and we had to define what those were. So every one of these is unitarily equivalent to a direct sum of copies of essentially a canonical Schrodinger representation. And so I will have to define that for you as well. Cool. Okay. Okay, so here's what I mean by a Seastar dynamical system, a G alpha Heisenberg representation, as opposed to just a G Heisenberg representation. So we have a Hilbert Seastar, Hilbert A module X. So X is going to be a full right A module. Hilbert. Rho is going to be a non-degenerate star representation of the C-star algebra in the dynamical system onto joinable operators. So we've got a C-star correspondence here, non-degenerate star representation. We've got unitary representations of our group G, which are strongly continuous. S is also one of these. I guess I should have put that there as well. So S is a representation of the contrary eigendual. We want these two unitary representations to satisfy the Weyl commutation relation. So Sx R gamma should be the scalar gamma applied to X, and then I'm allowed to switch the order of R gamma and Sx for all gamma in dual and X in G. And then the last two conditions are actually new commutation relations that are required in mine and Leonard's setting to have a uniqueness statement. So in this quadruple, we need to know something about how the representation rho of the C-star algebra interacts with the representations R and S of the group and its dual. So we actually want rho and R to be a covariant representation of the dynamical system that we started with. And I've run out of space. My students hate it when I do that. They're like, ah, I don't have any space left. Too bad. All right, and then I want the pair rho with S to be a, I'm gonna say it's a covariant representation just for symmetry, but I want it to be a covariant representation of this dynamical system where G hat is actually acting trivially. So really I'm just asking that rho and S actually commute as operators on the Hilbert A module X. Okay, so that's our general object, and these are what we're hoping to classify. And we want to classify them as some canonical object, which I'm going to define now, the AG alpha Schrodinger representation. So the first thing we need is a canonical Hilbert A module as opposed to a canonical Hilbert space, which in the previous setting was L2 of G. So we want a nice analog of that in this setting. We're going to build a Hilbert A module L2 of the C-star dynamical system AG alpha. And so all this is a completion of the continuous compactly supported functions from G to A viewed as a right Hilbert A module, or I should say inner product pre-Hilbert A module, where here's what the inner product looks like. So if I take the inner product of two vectors in here with respect to this, actually I should define the action as well. Sorry. So if I act on the right by an element of the C-star algebra, and I apply that to some group element G, I have f of x, but instead of the usual way that we would view CC of G A as a right A module, we're not going to just multiply on the right by A, we're going to twist A by alpha sub x. And then the inner product of f with G is going to be similar to the L2 inner product, except there will also be a twist by alpha x inverse. and we'll have f of x star g of x with respect to some hard measure on the group G. Okay, so that is our Hilbert A module that we are going to look to. Then we have a representation of the C-star algebra A. This is the natural kind of boring one. If I take an element of the C-star algebra and I operate on a vector in the Hilbert A module that we just built in the previous step, I'm just going to essentially scale and think of A as a constant function on the group G in the set of functions from G to A. Okay. And then last we have our unitary representations. So U sub X applied to a vector F. And F here is going to come from CC of GA. We're defining everything on that space. And then of course these operators will be adjointable and we can extend them up to the whole Hilbert A module. But applied to an element here of G, it will be a shift as before, but I'm also going to include a twist after the shift. And the representation of G dual is actually going to be exactly the same. So if I apply V gamma to vector F, that's just multiplication by the character V gamma. No twists or anything there. Okay, so we've got all of our ingredients for a concrete AG alpha Heisenberg representation. This particular one we're calling the Schrodinger representation, just like we had a Schrodinger representation in the classical setting. And none of this would really be okay, what Leonard and I have defined, if these two definitions did not reduce down in the appropriate setting to the classical case. Also, our Schrodinger representation, once you check everything out, is in fact in the broader class of AG alpha Heisenberg representations. All right, so now what I'm going to do is I'm going to kind of go back and forth between the classical proof, the proof of the classical Stone-von Neumann theorem, and Leonard's and my proof of this swelled up version. The very first step in the classical Stone-von Neumann theorem is to show that the C-star algebra cross product on the left-hand side is isomorphic to the compact operators on this canonical Hilbert space. And that isomorphism is happening from this integrated form of M with U, where M is the representation of functions as multiplication operators, and U is our shift operator on L2 of G. So this is uppercase U as opposed to our lowercase u on the Hilbert A module. Okay. So this ends up giving probably what's kind of silly now, but I'll write it, is that this isomorphism, we actually are going to want to view it going in this direction. So this is the inverse of that integrated form, which is an isomorphism to this cross product C-star algebra. LT, by the way, is left translation, the action of G on C0G by left translation. Okay, so we needed to generalize this. There were some tools already available to us to do this, so it wasn't too hard. So the first tool is this statement, a theorem within a theorem. If X, a general Hilbert module, if X is what's called a BA in primitivity bimodule, then you actually know that the C-star algebra that's acting on the left is isomorphic to the algebra of compact operators on the Hilbert module X viewed as a right A module only. And then we also have at our disposal Green's and Primitivity theorem. And Green's and Primitivity theorem actually tells us that this crazy, it's not that crazy, I guess, this very nice Hilbert A module that we constructed to be our canonical module for our Schrodinger representation tells us that this Hilbert module is in fact not only a right A module, but it's also a left C0 of GA in the cross product by the diagonal action left translation via alpha by the group G. So it's actually a left that module, and it's a right A module, which we already knew. And it is not just a C0 of GA crossed with GA bimodule, it is an imprimitivity bimodule. So that exact construction that we did comes up in Green's and Primitivity theorem. Okay, so that tells us that the isomorphism that we have in the previous bullet point holds here. So we actually know that our C-star algebra of this cross product is isomorphic to the compact operators on our Hilbert A module, viewed as a Hilbert A module, a right Hilbert A module here. But what we really need to know for our proof is not just that these two algebras are isomorphic, but we need to know what the map is. So map, or the isomorphism here, is actually implemented by, maybe not so surprisingly, an analog of this integrated form, the inverse of that integrated form, M with U. So instead of M, I'm going to introduce a capital C, and it's the integrated form of this operator with our lowercase u, which is left translation with a twist. Okay, and here C is a representation of the functions vanishing at infinity, taking values in C-star algebra A onto our, as adjointable operators on our special Hilbert A module by just left multiplying by our function f. Okay, and moreover, clearly if I said that we have an integrated form, one can check that the pair capital C with lowercase u is in fact a covariant pair for this dynamical system. The C-star algebra with this diagonal action coming from our locally compact abelian group. Good. So in the same way, we have a representation, really an isomorphism, from the compact operators on our right Hilbert A module to this cross product C-star algebra via the inverse of this integrated form. Okay, I just want to pause if anybody has any questions at this point. There's a lot of notation too, so I apologize for that.
This is using nothing about the C-star algebra. It can be any C-star algebra so far, yeah?
So far,
okay. That's
not right, exactly. So everything that has happened so far is valid for an arbitrary non-unital C-star algebra, but yeah, we're we're going to get to a place where we have to restrict, unfortunately.
And the restriction on G is just that it's locally compact and abelian.
Correct.
But it could be compact. That would also work.
Yes.
Okay, good.
Yeah.
Like that.
Thanks. Okay, so what happens in the classical proof of the Stone von Neumann theorem is that this, here, I'll say this. This C-star algebra, this cross product, it's like a little gateway C-star algebra. So basically, it is the intermediary step to connect things regarding the Hilbert space L2 of G with the arbitrary Hilbert space that you have selected for your Heisenberg pair, or I should say, yeah, your Heisenberg representation, so on some Hilbert space H. So this C-star algebra is acting as that intermediary. And the same thing in our proof, this is acting as the intermediary. So what we actually want is another representation that connects this to something having to do with an arbitrary Hilbert A module X. So we want to represent this as a jointable operators on the Hilbert A module X, where X is coming from our arbitrary Heisenberg representation. Okay. So here's how we build both of these. This is going to be of H. Okay. So in the classical setting, you get this really, really nice correspondence. If you have a G representation of your group, that was redundant. If you have a representation of your group that involves two unitary families R and S that satisfy the Weyl commutation relation, so you know that R and S have this really nice relationship, then you can actually build a covariant representation of that C-star dynamical system and vice versa. We only need the forward direction, so I'll only show you that construction. And here's what that looks like. So from this pair of unitary families, R and S, we can actually define a representation pi sub S from this C-star algebra to B of H. And the way we'll do that is we're actually going to define it on the inverse image of our Fourier transform. So I'm going to take something in this algebra, pull it back via the Fourier transform. And then once I'm back in the compactly supported functions on the dual group of G, we're going to hit it with the integrated form of the identity with the unitary representation S. So in other words, when we actually apply this to a vector F, we're going to see its inverse image under the Fourier transform, and it's going to be thrown in to this vector valued integral where we're integrating over the dual group. So this is the Haar measure for the dual group G. And so that's going to give us an element of B of H. What you have to check then is once you have this representation that depends on the unitary or in the unitary representation S, you want to check that this representation, you have the C-star algebra, is actually a covariant pair for the C-star dynamical system. I keep changing the order of my group in my action. It's okay, it's probably obvious which one is which. And just as a little side note, I guess an example, when you actually construct, do this construction for, when you do this construction for the unitary capital V, which is the multiplication operator by the character gamma, you recover the representation of C0G as multiplication operators. Okay, so multiplication operators. Cool. Okay, so what this gives us then is exactly what we were hoping for in the previous step. Hopefully this doesn't cause too much like dizziness or something as I'm just like scrolling quickly through this. Okay, so we wanted this thing in red and now we've got it. So we can take that covariant pair pi s with r, form its integrated form to be representation of that cross product C-star algebra. And now we've got a map coming from the compact operators on the canonical Hilbert space L2 of G all the way over to the arbitrary Hilbert space H, which we're eventually going to say, hey, this is the Hilbert space on which my R and S unitary groups are acting on. Okay, so Leonard and I generalized that construction. Again, I'm only going to show you the forward direction because that's all we actually need. So now we're starting with AG alpha Heisenberg. I have to kind of laugh because there's just like triples and quadruples all over the place. So the we have a representation of our dynamical system via this Hilbert C-star module X, a representation rho of the C-star algebra that the Hilbert C-star module is over, and we've got these unitary representations R and S of the group and the dual group respectively that form covariant pairs with rho. Okay, so in the same way, we're going to take the unitary representation S of the dual group, and we're going to build a representation of this C-star algebra out of it. So this depends not just on S in this case. I'm going to call it capital Pi, and I'm going to subscript it not just with the unitary representation, but also with rho. So this construction depends on both. And just like before, so let me say this is going to be a representation of our C-star algebra of functions from G to A that vanish to infinity to our given Hilbert A module as a joinable operators on that Hilbert A module. And here's what it looks like. So we will pull things back along the generalized Fourier transform. So we will precompose with the inverse of that, pull things back to the compactly supported functions from G dual to the C-star algebra A. And once we're there, we will apply the integrated form of rho with S. So effectively what we're doing is when we apply this to an element of C0GA, we see the inverse Fourier transform of that function applied to gamma. We take rho of that because that's a C-star algebra element, and then we average over the unitary group S gamma. And this gives us an element of, gives us an adjointable operator on the Hilbert C-star module X. Okay. The thing we need to check, of course, is that this, this representation is actually a covariant representation of the C-star dynamical system. I won't say it out loud, this one. And it is. Okay. And as an example of what this construction does to something that has concrete rho and S, when rho is our capital M where M is taking elements in the Seastar algebra to essentially constant multiplication by constant functions on CC of GA. And we're looking also at little v, which is multiplication by the character gamma. What we get when we do this capital pi rho S construction is we get capital C, the representation of the Seastar algebra C naught of G to A as multiplication operators on our imprimitivity bimodule L2 of the Seastar dynamical system. So this is the multiplication operator representation, where we're taking things in here to act on things in here. F gets mapped. Maybe I'll do this. So for anybody in the dense subspace of our Hilbert module, F applied, CF applied to G is FG. It's the natural representation. Okay, so just as in the classical case, we were hoping that we would get a representation from that cross product Seastar algebra as a jointable operators on any Hilbert Seastar module X that we wanted, so long as it was part of a Heisenberg quadruple. Okay, and now we have that. Okay, so here we have that this is the integrated form of rho with S and R. Okay. All right. And then just to point this out, because this will be important later, I didn't verify this for you, but the fact that this capital C representation is actually our construction using M and V, we can also replace capital C here with our other notation. It'll be useful later. Okay, so the reason why this is important and the final step in the classical proof is because in the Hilbert space setting, we actually know something about non-degenerate representations of compact operators. These are special. Okay. So in particular, if you have a non-degenerate, and I put Arvis in here, I was corrected earlier on. So this result appears in Arvison's invitation to Seastar algebras, but it more than likely existed prior to Arvison. So yeah, doesn't matter. Okay, every non-degenerate star representation of the compact operators on the Hilbert space is actually unitarily equivalent to potentially a direct sum of copies of the identity representation. So basically, if we have the compact operators on a on some Hilbert space H prime, and we represent that algebra to act on the Hilbert space H, then if I instead look at some copy of the identity representation, so now we're down here acting on a whole bunch of copies of the Hilbert space H prime, what this theorem says is these two representations, there is some number of copies of the identity representation that intertwines the representation that you're given. Maybe I'll call this psi. And this is a unitary equivalence. Okay. So for us, the representation that we care about is actually where H prime is L2 of G, and psi is the big composition of those integrated forms. So this would be pi s r, this is in the classical case, composed with m and its integrated form of capital U. So we built that representation for the classical Stone-von Neumann theorem, and the final step here is essentially that we can untwist all of that to get that representation psi is equivalent via unitary to direct some copies of the identity representation, and a bunch of untwisting happens, and you get unitary equivalence of the unitary representations S and R with the canonical ones U and V. So what Leonard and I needed is some sort of a similar result. If I have a representation of my Hilbert module X as adjointable operators on, let me call this instead X prime, as adjointable operators on this Hilbert module X, then what we really would like is to have the exact same result. There's some number of identity representations down here onto a direct sum of copies, into a direct sum of copies of that algebra. And there's always a unitary that conjugates those representations. So this is the part where we had to restrict our Seastar algebras. So no longer could X prime be just an arbitrary Hilbert A module. It has to be a Hilbert K of H module. And we're not sure if this can be generalized. It's possible, but we didn't see a way to do that. So here's what we got along the way. And this generalizes the results at the top of the page, this one. So every non-degenerate star representation of the compact operators on a Hilbert K of H module X is in fact unitarily equivalent to a direct sum of copies of the identity representation. So what that gives us is exactly what we needed. We have a representation of our compact operators on that Hilbert module, and now I will write everything down and I'll start crossing A's out and putting in K of H's and R's where the G's are. But we have this representation to L of X via the composition of this integrated form and the inverse of this other integrated form. Okay, and it turns out that we can get, I'm going to put a smiley face there. We can get a unitary that that does what we need it to. Okay, only in the case where A is compact operators. So let me replace this with K of H. This has to be the real numbers now. All right, so in conclusion, what that does for us is it allows us to untwist the composition of those two integrated forms. Those two integrated forms involve the unitary representations S and R, and the other one involves the unitary representations U and V. And the untwisting process follows from some uniqueness statements about integrated forms. So we have that this composed with this thing's inverse is unitarily equivalent to some direct sum of copies of the identity. And so this integrated form is unitarily equivalent via some unitary W to a bunch of copies of this integrated form. Untwisting gives that rho is actually unitarily equivalent to some number of copies of M. S is unitarily equivalent to some direct sum of copies of V, and R is unitarily equivalent to some direct sum of copies of U. And that is the covariant Stone von Neumann theorem's conclusion. So I'm out of time. I just wanted to maybe touch on some of the stuff that Leonard and I are looking at. As I said before, we're hoping to use this in the same way that people have for a long time been using the classical Stone von Neumann theorem to classify pairs of self-adjoint operators that satisfy the Heisenberg commutation relation. We also would really, really like to have this result for more general Seastar algebras. Obviously, K of H it's a great Seastar algebra and all, but we would like to have a lot more than that. And then also we would like to be able to do something for locally compact non-abelian groups. And then someone suggested to us that perhaps even looking at some sort of a setting with coactions and quantum groups, that for certain quantum groups, we might be able to extend these results to that setting. So thank you.
Clap, clap, clap. So yeah, thanks very much. That was a really nice talk. Are there any questions in the audience? Everyone should be muted, so make sure if you ask something to unmute yourself. Yeah.
Hi, Maria Stella.
Hi, Lara.
Sorry.
So sorry, did you hear that question, Lara?
Oh, no, I didn't.
Oh, I can't hear you all of a sudden. Huh.
Whoa. Okay, hold on.
Okay, now I can hear you again. Maybe that
You can? Okay, sorry. No, I didn't hear that question.
Okay, maybe Ray, you can ask it again.
Sorry, if you are speaking, I can't hear you. This is very strange.
I can't hear you either, Ray. Are you close to Karen? Can you...
I can hear you, Tristan.
Okay, well, that's good. But yeah, I can't hear Ray either. Maybe Ray can use Karen's computer if he's nearby, or...
Okay.
Hello. Yeah, I can.
Amazing technological.
It's so fun.
The upgraded version of Zoom. So if you've got unbounded what you have is these sort of unbounded differential operators in some sense on your Hilbert modules. If they form one of these Heisenberg pairs, can you say anything about their relation? Would they give you like K or classes in KK theory?
So this is a goal of mine, is to know anything at all about KK theory. I wish I could answer your question. That's a direction that Leonard and I are hoping to go towards, because we know that there's such a strong connection, but I'm sort of breaking into the Hilbert Seastar module game right now. So yeah, that's a great question.
I was wondering if you'd, yeah, maybe something like UHF algebras would be a reasonable thing to try, because I think they should have something similar, you know, since they're just direct limits of matrices. This
Right.
Their equivalence sort of thing.
instead
Well,
of compact operators. Yeah, we thought maybe, I mean, we're not really sure that this will yield any more interesting examples, but perhaps just looking at Seastar algebras that are Morita equivalent to compact operators. It's probably just a simple question. Is there anything else there? If anybody knows a quick answer to that question. Is it just direct sums of copies of compact operators, or is there other stuff that's Morita equivalent to those?
okay. Any further questions? I'm trying to look at the chat as well. It seems not. Yeah, I was also going to ask you if you were planning to look at non-abelian groups, and then I guess you obviously have to replace all your G hats with the Seastar algebra, group Seastar algebra.
Right.
And that of course just like, yeah, makes the quantum group question kind of natural. So that would be nice. You could do that for some of the nicer behaved like quantum me groups or something.
Right. Yeah, that's, and so like that right now, since we're working in just the unbounded, we're kind of probably going to come back to the Stone von Neumann theorem question, but we're kind of an unbounded operator land / held. So we're like, so I think we'll come back to this, but definitely the non-abelian question, that might take a while.
Is that done even in the non-covariant version so far?
You know, that's a good question.
Well, for that matter, for quantum groups, I wonder, yeah, if it's
Right.
the non-covariant version.
Feel like I'm taking notes for like things. It's very helpful. I really like, these are very great questions. Thank you. Cool.
Oops. All right. Do we have any other questions? Sorry, I muted myself again. Obviously, we're technological idiots here. If there's no other questions, then maybe we can thank Lara again with the poor excuse for clapping. That is the Google or Zoom reaction. But yeah, no, it was a really great talk. I really appreciate that you got up early for us.
Thank you guys for having me. Oh wait, you're muted again, Karen, I'm sorry.
Steal your screen sharing ability for a second.
Oh,
so I can
yeah, please.
announce our next speaker, which I should have somewhere. Our speaker next week is going to be Bob Yunkin from Clermont-Ferrand, and he will talk about pseudo-differential operators. So we'll be going more in the non-commutative geometry direction next week. And I hope that some of you will, again, join us. So thanks very much for coming, and see you hopefully next week.
Bye, everybody.